Greetings, dear colleagues, and welcome to this first webinar on a series on gypsiferous and calcareous soils. That such soils pose a special challenge to researchers. And this is an initiative of the GLOSOLAN Soil Laboratory Network and the International Network of Salt-Affected Soils. So we are co-hosting this webinar that has been especially developed as well with the collaboration of the NENA lab. First, I want to introduce you to the persons that we have today here, just names, because we have our coordinator in the NELA lab, Karim Sabatsi. We have Isam Barra from FAO, and we have as well Maria Kuniuskova, you know very well, Professor Rosa Poch, that will be our speaker. Then I will pass the floor after welcoming all of you to Professor Karim Sabatsi.
Hello, everyone. Good morning, good afternoon, or maybe good evening, everyone joining us from around the world. It is my pleasure to welcome to all to this important webinar entitled Introduction to Calcareous and Gypsiferous Soil Challenges and Solutions. This webinar is the first webinar in the webinar series focusing on calcareous soils and gypsiferous soil. So these kind of soils are critical to agriculture production in many regions, especially in arid and semi-arid zones. But yet they remain understudied and undermanaged in many contexts. This series is a part of our shared mission at GLOSOLAN and INSAS to build capacity, share knowledge, and strengthen collaboration on soil issues that are vital for food security, environmental sustainability, and climate resilience. Can I share my screen for present my presentation? Maria, is it possible? How can I do that?
In the bottom, you can see the button, share.
Yeah. Do you see my screen?
Yes.
Yeah. Sorry, should review. So, as all of you know, the importance of soils in many ecological services and food security and climate change, and we need to manage soils for provide sustainable services. If we want to manage the soils, we need accurate and if we are going to manage the soil for sustainable services in food security, so ecological services or climate change and so on, we need accurate and harmonized data in local, national, regional, and global scales because many issues in the harmonized data or accuracy soil data in all of scales, regional or national or global scales, The Global Soil Laboratory Network, GLOSOLAN, has been established 2017 to build and strengthen laboratory capacity in soil analysis to respond to the need for harmonizing methods, harmonizing data, and try to upgrade the standard of laboratories, so laboratories analysis for accurate data. What we are going to focus on the calcareous and gypsiferous soils because this kind of soil rich in the calcium carbonate and gypsum. This kind of soils widely spread in many regions, and this kind of soil is very important in the agriculture production, especially in arid and semi-arid regions. But they present many challenges in the physical, chemical, biological properties that pose to challenges in the manage and sustainability and land use in this area. Because of that, we are going to provide actionable insight for characterizing, managing calcareous and gypsiferous soils. And because this kind of soils present, for example, many issues, for example, nutrient deficiency, water movement, and also difficulty reclamation and sustainable use. But this kind of soils offer the opportunity if we equip with our right science and with the equipment for solution this problem. So in this for this reason, these webinars aim to improve the understanding analysis of calcareous and gypsiferous soils, explore the challenge and new testing method, and also share best practice and promote global and collaboration in soil scientists. For this object, today we are starting the first seminar on the calcareous and gypsiferous soils. I should say thank you, Rosa, Professor Rosa Poch, that accepting our invitation to present this webinar in characteristics, challenges, and innovation in this kind of soil. In second webinar, we will dive into lab analysis measurement challenges, for example, pH, electrical conductivity, heavy metal, calcium exchange levels, capacity, and so on. You know that this kind of soils in arid and semi-arid soils affected by storm and chemical analysis face problem. We should have some solution for this kind of analysis in this area. In third webinar, we will focus on physical and biological properties and analysis. This season will cover, for example, structure, texture, compaction, porosity, and implication for microbial activity on analytical procedure will be shared. In all of these webinars, also we will discuss about GLOSOLAN SOPs, standard operation procedure, and we will focus on quality control, health, safety during the implementation of these SOPs, like pH, nutrient availability, calcium exchange capacity, and so on. And in the first webinar, we will discuss about right chemistry, analytical, technical in characterization of calcareous and gypsiferous soils, especially we will focus on the soil spectroscopy. Maybe we carried out a special webinar in this method, using this method for characterizing calcareous and gypsiferous soils using soil spectroscopy. We are thinking about, and finally, in the last webinar, we will bring it all together by addressing major problems and sharing case study on how these soils can be improved and manage sustainability. I hope that this series of webinars, I believe that it can be helpful for many stakeholders, so scientists, agronomists, or laboratory managers, technicians, especially in the laboratory experts, agriculture consultants, and land manager, environmental researchers, and also university students. We hope this comprehensive webinar series on the analytical methods of calcareous soil and gypsiferous soil provide a valuable platform for sharing knowledge, addressing challenges, and promoting sustainable land management practice. We begin today's webinar, and deeply honored to introduce Professor Rosa Poach from University of Linda. I hope that spelled very well pronunciation. A distinguished expert in soil scientists, she will be presenting calcareous and gypsiferous soil characteristic, challenges, and innovation. Professor Poach, thank you very much for accepting our invitation and for being with us today. We are eager to learn from your extensive experience and insights. And also thank you again for joining us, all audience. Let us now welcome Professor Rosa Poach. Floor is yours. We are waiting to hear from you. Yeah, thank you.
Thank you very much, Karim, for this introduction. I hope that you are getting me well. And and thank you very much for inviting me to, thank you very much for inviting me to give this seminar. And as Karim has said before, I will give an overview of calcareous and gypsiferous soil, and I will deal briefly with some of the chemical properties, agronomical problems that they have, also advantages, and so on. I think that some of these parts will be taken care by the next speakers in the next seminars. Okay, I don't know if I can share my screen at this point. I think that this screen should be disconnected now. I don't know how to do that. Yeah. Can you please stop sharing?
Professor Karim, you must stop your screen sharing.
Stop sharing.
I stopped sharing now. Just let me know it's stopped, but I don't know. I don't.
It's in the upper part.
Familiar with this kind of.
Now.
Is it okay?
I think that now it's okay. Thank you very much.
You are welcome.
Okay. I will start then to speak about about the global and regional overview of calcareous and gypsiferous soils. My name is Rosa Maria Poch, and I come from the University of Lleida in Northeast Spain. So we have Mediterranean climate, and we do have many calcareous and gypsiferous soils. This is the index I will follow according to the suggestion of Maria and of Jorge. definition, analytical application challenges, agricultural margin implications. I will not speak much about potential solutions and innovations because, yeah, we have what we have, yeah, and the traditional management of these soils have been, yeah, for the centuries, and yeah, there are potential solutions regarding, for instance, availability of phosphorus and iron, but yeah, there is nothing very, very new on this field. Yeah, so I will try to cover this aspect. And I will start with calcareous soils and then gypsiferous soils. Something I wanted to say is that both types of soils are very widespread, mostly calcareous soils. If you see here the distribution of the amount of calcium carbonate equivalent around the globe, I mean, we have like more than half of the land that is covered by these soils, because yeah, you know that this projection of the globe is, I mean, it exaggerates the surfaces at the higher latitudes. So, and it's very interesting. Sometimes I have thought that if the first soil scientists were coming from this area of lower latitudes, of Mediterranean, of more arid areas, they would start with calcareous soils as the normal soils, yeah, and not with silice classic soils or soils based on silica, yeah, because they are really abundant. They are not a curiosity. No. They are the soils that we have, yeah. And if we see the distribution of calci soils, yeah, it responds also to the previous map, where you see that, yeah, the distribution of calci soils, it means the soils that have movement of carbonates, yeah, that have a calcic horizon, it's quite extended. But I mean, the calcareous soils is more than that, yeah, because an empty soil with calcium carbonate is also a calcareous soil, and it's not represented here, yeah. So we see that they are really very, very widespread, yeah, around the world. Good. What are the characteristics of calcium carbonate, calcareous soils? That they contain calcium carbonate. That the main mineral is calcite. There are other minerals, yeah, in mineralogy that respond to this formula, but they are, for instance, aragonite that is not common in soils, yeah, the case and so. So in soil environments, we'll find calcite. And this is the famous equilibrium carbonate bicarbonate, by which calcium carbonate is guided. So all the dynamics of calcium carbonate respond to this equilibrium. So we see that calcium carbonate, that is, wait, I think that the pointer, yeah, no, sorry. Yeah, here. We see that calcium carbonate, yeah, its dissolution is a bit anomalous. Why? Because calcium carbonate needs CO2 to be dissolved. Yeah, CO2 from the atmosphere or from the respiration of roots generated by microorganisms in the soil. So calcium carbonate plus CO2 plus water dissolves, and then this is liquid. These are two anions of bicarbonate and water. Yeah. Okay, so this is the famous equilibrium. Since this is limited by the amount of CO2, this equilibrium is quite constant in the soil because it's ruled by the amount of calcium carbonate in the atmosphere. Yeah, and so the pH of all calcareous soils in equilibrium will be around between 7.5 and 8.5 because it's the pK of this reaction. Yeah. Okay, this is what happens in calcareous soil. So we'll have some dissolution of calcium carbonate and some precipitation depending on the amount of water and CO2. But there are soils where the parent material is not limestone, has no calcium carbonate, but they contain calcium carbonate in arid areas, because we have seen that many calcareous soils are in arid areas. Yeah, in wet areas, all is dissolved. Yeah, In arid areas, if we have calcium that comes from weathering of another rock, for instance, from plagioplaces that contain calcium, yeah. Sorry, I have to. Then what happens is that the CO2 of the respiration of the biota in the soil combines with water, forms bicarbonate, yeah, and bicarbonate plus the calcium coming from another mineral, the weathering of a mineral, is forming calcium carbonate, yeah. So it results on existence, precipitation, new formation of calcium carbonate in those soils that do not contain calcium carbonate in the parent material, yeah, due to the formation of bicarbonate and the presence of calcium from other sources, yeah. Okay, so we see that in this equilibrium, in these reactions, there is a strong influence of biological activity. It means that in soil environments with a lot of biota, dissolution of calcium carbonate is promoted, yeah. That these soils appear in warm areas with limited precipitation, otherwise calcium carbonate is leached out of the profile. So as a consequence, it appears in the soil moisture regimes of the soil taxonomy, acidic, xeric, and eustic, yeah. Its solubility is quite small, 5 to 6 milligrams per liter, but it varies, yeah. And that, as I said, the pH is buffered between 7.5, 8.5. And since the soil solution is full with calcium ions, that is a divalent ion, the structure of the soil is very good, yeah. So we have strong structures if we have enough clay, of course, because you need clay to be flocculated, and then yeah, normally you have well-developed structures. And as you know, in the field we detect it with chlorhydric acid at 11% or 10%, and then it bubbles, yeah, when when we have calcium carbonate in the soil. And another anomaly in the solubility of calcite is that with increasing temperature, the solubility of calcium goes down, yeah. Normally, the solubility of any salt increases with temperature. In calcite, not. Yeah? It has relevance for calcareous soils in higher latitudes that they suffer glaciations, yeah, during the Quaternary. The glaciations, melting water from ice, is very, very effective in solubilizing calcite. So decarbonation is easier in these environments. Good. So we have seen that we would find calcareous soils mostly in these environments. Yeah, environments where you don't have leaching moisture regimes. Yeah, as soon as we have some excess of water that goes down along the years, we would have removal of calcium carbonate. Okay. The models for the formation of calcic horizons, or for the accumulation of calcium carbonate in the soil, there are basically two. Yeah, the most common case in our dry semi-arid environments is this one. Yeah, so we have an upper horizons with roots with biological activity. In these horizons in the soil, you have a high partial pressure of CO2 because you have biological activity with heterotrophic organisms that release CO2 by respiration. Yeah. So it means that we will have promotion of dissolution of calcium carbonate, as we have seen in the first reaction. It goes down the water, and at a given moment, yeah, calcite precipitates because roots do not reach this point, and then we have the precipitation of calcium carbonate in depth. Yeah, this is a normal case by per descensum or vertical leaching model. But there are some cases where we have a water table saturated with bicarbonate and bicalcium, so water table that is coming from watersheds or basins that have limestone as biomaterial. And then this water table results or makes that the soil air is saturated with CO2 in the nearby this layer. Yeah. So as water table oscillates, yeah, we will have precipitation of calcium carbonate here. Why? Because if we have, for instance, in the upper horizons, the partial pressure of CO2 will equilibrate with that of the atmosphere. So we will have some precipitation of calcium carbonate in the oscillation area of the water table. Yeah. And this can happen also in wetter environments, yeah, where you don't have a completely leaching environment, but you have stagnation of water at some depth. Good. Some pictures. Yeah, dissolution of limestone. All of you that come from limestone areas know this. These special features of the surfaces of the limestone near the surface. We see that the shapes of the rocks are never very angular. Yeah, so everything is very rounded with the paths of the water when it runs over the rocks and make this special relief of morphology. Yeah, here with the words that we use in different languages. Then the horizons with carbonate accumulations, with calcium carbonate accumulations. So when this calcium carbonate moves and precipitates at a given depth, they are called both on the WRP and the USDA. They are called calcic or petrocalcic horizons. Calcic when you have an important accumulation, so more than some threshold. Then you have diffuse accumulations and horizons with friable nodule rhizoccretions, different type of calcite accumulations. And if the accumulation progresses and goes further until all the voids are filled with calcium carbonate, then we have cemented petrocalcic horizons, Bayesian horizons. We'll see some pictures of that, but I'm sure that all of you know of them. Here you have the famous pseudomycelia. This is believed to be the first step in precipitation of calcium carbonate in the pores of roots or of channels of fauna and so on. Yeah. Some of them are more complicated. It's not simple precipitation, nothing else. Some of them are calcified roots or calcified hyphae of fungi. Yeah. But yeah, this webinar is too short to delve into the dynamics of this process in the soil. Let us say that this process is chemical, but also biological. So microorganisms have also a lot to say within these accumulations. Yeah. Pseudomycelia are not diagnostic for calcium carbonate accumulations and for defining a calcic horizon. Why? Because some of them are formed very, very quickly. For instance, if you open a pit and you leave it, and it rains and you leave it a couple of 3 days, you go there and you'll see some precipitation of calcium carbonate. So if it is removed with water, you get a specimen, you put water and the crystals disappear. Yeah, these are pseudomycelia that are not diagnostic for diagnosing calcic horizon. Other accumulations. These are very nice rhizoccretions or carbonate nodules, hard carbonate nodules in some paleosols from Mallorca, in some field dolites. And in this case, you see clearly that these nodules were old roots and calcium carbonate precipitation along old ancient root pores. Yeah, and they have yeah, more or less rounded shapes, yeah, and sometimes you can find even a pore inside them that is the original channel, yeah, and they are baked sea horizons of compressions, yeah. You can have also some soft carbonate nodules. Yeah, that would be the first step on precipitation. It's just a concentration of calcium carbonate around the point where the this equilibrium carbonate by carbonates is changed, and then calcium carbonate precipitates there. Yeah. This is also a BK horizon. Yeah. And also, you know that in very stony soils, you will have these carbonate pendants. Yeah, so this precipitation of calcium carbonate in the lower part of the gravels. This is very common in all river terraces. And this will be also decay horizon. And finally, you have BKM horizons when all the pores are filled with calcium carbonate, and then you have these massive, strong accumulations of calcium carbonate that look like a rock. Yeah, this is not a rock. This is an horizon. Yeah, this is from nearby our campus, and this is from Mallorca again. Yeah. To test carbonate cementation, yeah, both USDA and WRB give rules for testing it with a slacking test. So you have to get a specimen, put it in water, and see if after an hour, or after 24 hours, it depends on the system, it slakes or not. Yeah, this is the test for cementation. And you can understand very well that this BKM horizon is a problem, so it limits the rooting depth of the soil. Okay, this is the model of formation of petrocalcic horizons. Yeah, this model was first established in New Mexico, by Geil and others in the 60s. And it has been tested and proved in many other places in the world. Yeah, and it presents the evolution of the accumulation of calcium carbonate. If you have a continuous accumulation of calcium carbonate in the soil, you get in fine-grained biomaterial. First, you have these filaments, after the nodules, after everything is clogged, and since the hydraulic conductivity is diminished, you have stagnation in water at the upper part, and then you get a laminar layer on top. Yeah, if you remember, this is the same morphology we got here. Yeah, so laminar layer and petrocalcic horizon. In this case, is recarbonating an old BT horizon, not arterial horizon. Yeah, so in coarse grained parent material, you get first these pendants. Afterwards, all the coarse material is coated with calcium carbonate. You get also clogging of pores, and finally you get the same morphology. The stages 5 and 6, they are already karstification and degradation of this horizon when the supply of calcium carbonate is not more active. Yeah, you get these stages in very old terraces that are isolated with the source areas. Good. Go to the agricultural management implications. Iron chlorosis. What is iron chlorosis? The deficiency of iron of many plants due to the precipitation in the soil as iron carbonate. Iron carbonate is very insoluble. So plants cannot absorb, cannot get iron for their functions. There are some plants, some crops that are quite sensitive here. For instance, we have strawberries. You have here peaches, yeah, and here you have vineyards, yeah. So these plants, at least in my area, at the end of summer, you go to the fruit orchards and you see many trees that have this deficiency, yeah. So the way to deal with this problem is first try to use crops that are less sensitive to this. Yeah. If you have to plant these crops, then it will be necessary to apply iron as chelate. Yeah, sequestered iron. Yeah, it can be applied either foliar application or to the soil. Yeah, and then the plants can get the iron that is chelated. Yeah, that is not immobilized. Or, for instance, use chlorosis-resistant cultivars. They exist in vines, in vineyards. You get the stalk of the tree, also in fruit trees, in peaches. There are some stalks that are resistant to hydrochlorosis. So you have to select in the market which are best to grow your cultivar on top. Okay, another element that is retrograded is phosphorus. Yeah, why? Because again, it precipitates with the cation, yeah, as calcium phosphate that is also very insoluble. And then we have deficiency of phosphorus as these purple colors around the leaves or short stems. Yeah, these are the typical symptoms of phosphorus deficiency. Yeah, and the solution is to use superphosphate fertilizer. So it's not phosphate, but hydrophosphate. Yeah, so some water, some hydrogen here. Yeah, and less calcium. Yeah, so these compounds are more soluble. Yeah, and the plants can get this phosphorus easier. Physical constraints, as we have said. Well, physical constraints, before going to this, there are not many physical constraints in calcareous soils. Why? Because indeed we have seen that soils have good structures. It's very easy to get a good structure in calcareous soils. Yeah, to the point, now I'm making a parenthesis, to the point that when defining cambic horizons in soil taxonomy, for instance, if the material is calcareous, you need to, so the structure is not enough to define cambic horizons. You need to demonstrate that calcium carbonate has moved. Why? Because it's very easy to get a structure in calcareous materials because of the presence of ambivalent cation as calcium. So, physical constraints, we find that when we have a petrocalcic horizon, we have, in fact, a limitation of the routing layer, of the routing depth. So, solutions to that, historically, look at this, what people did here in Mallorca, and also in Catalonia, there are some places that they did that. They removed the calcium, the petrocalcic horizon in some parts. Can you imagine the work to do that? Yeah, of our ancestors. Yeah, very strong. But in this way, you get better rooting conditions for the plant that you put here. Yeah. Problem with that, if you flow depth with the calcium with a petrocalcic horizon, you will have an increase of stoniness in your soil. Yeah. Here is, they have broken also this petrocalcic horizon, and then maybe they will plant some trees here. Yeah. Some other places they get these pieces of petrocalcic horizons and they put them as walls, yeah, around the field. Yeah. Some bench terraces are made with petrocalcic horizons. So it's why I have put here plowing, yes or not. I would say no. Don't plow it, don't plow because it's a lot of effort, and also you will have an increase of stoniness in your soil. Yeah, but in some cases it has been done. Analytical and classification challenges. Well, very shortly, diagnostic. Well, this is a calcic. Well, this is a Chernozem, calcic Chernozem in Hungary, yeah, with nodules of calcium carbonate here. The diagnostic are either calcic and petrocalcic horizons, as we said, and in WRV, you have calcaric material. Calcaric material, it does not mean anything, just that this material has calcium carbonate. Yeah? And soils, in soil taxonomy, it goes to the suborder level with, for instance, calcites, calciferous, or calciferons. Well, this is suborder and this is group, sorry. These two are two groups because the suborder is here, or xerol. And WRV, you will have calci soils, the soils with a calcic horizon or petrocalcic, and then you have the calcaric qualifier in other referential groups. Analytical and classification challenges. Good. How we analyze calcium carbonate? We have, for one side, we can analyze the calcium carbonate equivalent. Yeah. Why do we call it equivalent? Because we measure in the lab the amount of carbonates released with chlorhydric acid. And this chlorhydric acid also releases CO2 from magnesium carbonate, from dolomite. Yeah. So, but we express it as calcium carbonate, and is why we call it calcium carbonate equivalent, because all the CO2 released, we calculate it as calcium carbonate. Yeah. Okay, and then we measure it normally with a Werner calcimeter. So the amount of CO2 that is released after application. Okay, then we have active line. What is the active line? The active line, well, imagine that you have calcium carbonate, but you have it in sand or in gravel. Okay, this calcium carbonate will be not as reactive in the soil, yeah, as the calcium carbonate that's very fine. So the active line is the fraction of calcium carbonate less than 50 microns, yeah, and is the one that gives us problems, for instance, of deficiency of iron or deficiency of phosphorus. Yeah. So there are these methods. It's a fine fraction that reacts with a solution of ammonium oxide. Finally, 2 points important that I suppose that I will be dealt with in the next webinars. Do not remove carbonates before doing the textures, because if you have 40% of carbonates, it's nonsense to remove the carbonates. Yeah. So by convention here in our lab, we never remove carbonates. Yeah. Why people remove carbonates in other places before making the particle size distribution analysis? Because calcium is a divalent cation, and then it tends to flocculate the clays, so you don't get the dispersion. But the solution is to add more sodium extra metaphosphate, and then you do the texture perfectly. Yeah. Another thing that we have to be aware of is that when we analyze the cation exchange capacity, yeah, when we leach the sample with ammonium acetate, we are also dissolving part of the calcium carbonate. So in the leachate, we'll have calcium that does not come from the exchange complex, but from the calcite. So since these soils will have always a CEC of 100%, we calculate calcium by subtraction. Yeah, so use some sodium, potassium, and magnesium, and then you subtract it from 100, and then you get the exchangeable calcium. Okay, until now, regarding calcareous soils, yeah, after in the question session, you can ask me about it. Let us go to gypsiferous soils. Well, this map of gypsy soils, yeah, taken from the same source from FAO, shows that where do we find gypsy soil? We find gypsy soils also in arid areas, yeah, and also in less places. Why? Because gypsum is very soluble, more soluble than calcium carbonate. So it will be much easily leached out of the profile. Yeah. Again, this is the distribution of gypsy soils, but you have also some empty soils on gypsum rock, yeah? And then these soils have also gypsum, but they are not gypsy soils. So the actual area occupied by soils with gypsum, by gypsiferous soils, is larger. Good. Here you have the solubilities of calcite, more or less 5, 6, of gypsum. Gypsum is calcium sulfate plus 2 molecules of water. And the solubility is 2 orders of magnitude or 3 orders of magnitude more. It's 2.6 grams per liter. Yeah. And if we compare it with halite, yeah, it's much higher. Yeah. So gypsum is not a soluble salt. Yeah. It's something in between. Yeah. So gypsum will not create salinity in the soil, but has a solubility that is much higher than calcite. Yeah. It results in an electrical conductivity of the extract and also of any electrical conductivity of any relation soil water, yeah, will be 2.2 decisiemens per meter at 25 degrees. So the threshold is 4 decisiemens per meter. So soil with gypsum are not saline. Please remember this, because the first soil classification systems considered gypsum as a salt. Gypsum is not a soluble salt in the way we consider them in soils. Yeah, they will not cause salinity to plants. Another characteristic of gypsum is that at more or less 50, 70 degrees, it starts to lose some hydration water. So we'll have another mineral that is called basanite when we have half molecular water, and another mineral that is anhydrite when we have calcium sulfate without water. This process will occur in very, very hot climates. Yeah. And also we'll find anhydrite sometimes as parent rock, yeah, some anhydrite that has not undergone weathering of the rock to convert to gypsum, yeah. Normally we'll have gypsum in the soil, and as I said, in very, very rare environments, in very hot environments, we can have sometimes basanite. Besides that, these temperatures are telling us that when we send samples to the lab, yeah, please do not heat them, do not put it in the baffle at 105 degrees. Do not dry these samples at 500 degrees, because then you will think, this sample is very wet. No, it's not wet, because it has lost water from the gypsum that is not moist water, yeah? So these samples always dry them at room temperature or at 40 degrees until constant wait. Yeah. So wait one day, put again in the oven at 40, and then wait again the day after. These days are the constant wait, then you can analyze them. You can do your analysis there. Okay, there are also some, well, since we talk about field recognition of calcium carbonate, how can we recognize gypsum in the field? Because sometimes when you have filaments or so, it's difficult directly with the hand lens, you can get something, but it's better to make these tests. In this test can be done in the field. Here it's in the lab, but you can do it in the field if you get some test tubes and these solutions, yeah, of nitrate, silver nitrate and barium chloride. Yeah, you get some pots of that, some tubes and some distilled water. You get some soils here. You put some water. You shake it, and then you test it with this. And I will show you, for instance, these are chlorides. Yeah. These are sorry. None. There were, well, I'm suppose that you will have the, now I don't know how to remove the laser. No, I don't know. Anyway, there was some short movie, yeah? So I will explain you. You put some drops on here on the leachate, on the filter, and then you will see a cloud, yeah? And here also for sulfates, you will see a cloud when you put a drop of barium chloride, yeah? So it's so easy that you test it in the field, and then you will be sure if there are sulfates, this material that you have dissolved in the test tube will come with gypsum, most probably. And also for saline waters or for saline soils, you can test for chlorides with silver nitrate in the same way. Origin of gypsum. Yeah, as I said to you, they are either evaporites, yeah, from the tertiary, from the quaternary, the parent rocks that have gypsum, yeah. It can come also from the groundwater, from the water saturated with calcium and with sulfates coming from these areas with evaporites, or maybe wind blown, yeah, because in these arid areas you have a lot of dust coming from desert areas with gypsum, and then we can have wind blown gypsum in our soils, yeah. Another source is in acid sulfate soils. I will speak very shortly about that, but you find gypsum also in acid sulfate soils under any climate. Yeah, this also is particular. Some pictures. Parent rock, gypsum parent rock. This is in the Alps. Yeah, gypsum in the Alps. You see that it's completely karstified. Yeah, completely rounded, lot of holes because it is very quickly dissolved. Yeah. In our area, this is near near the place where I live. This is also gypsum rock. Yeah, this is not leached out of the environment because the climate is semi-arid, and you get these flat valleys, yeah, enriched with gypsum. Yeah, so the gypsum is leached here from the slopes. Also, there are sometimes some mass movements because microcrystalline gypsum is like a mud. Yeah, when it gets saturated, it can flow as a mud flow to the dry valleys. Yeah, and also you find it in dry lakes in cepas. Yeah, this is in North Africa. Then in these lakes, normally you have a zonation of so in the middle of the lake you find soluble salts, normally chlorides and other sulfates, and then you go to the margins, you find gypsum, and then at the very margin you find calcium carbonate because it precipitates as it goes into the water goes into the dry lake. In these places, you find polygonal gypsum crust. This one is from Australia, from Lake Eyre. And here you have also polygons here, yeah. And here is a feature that is very common because, you would think that in these soils there is nothing, there is no life. But no, it is not true. In these soils, there is a lot of life because these soils hold water, and then all the life in this environment is under the soil. Yeah, so you have a lot of faunal activity in these soils. Again, the way we find it in soil, we have this gypsum crust. Yeah. Then in the field, we have also vermiform gypsum. Yeah. This is the equivalent to the pseudomycelia of calcium carbonate. But normally these accumulations are thicker. The color is whiter, than the one of calcium carbonate. When you see it with the hand lens, it's like sugar grains. Normally this gypsum is lenticular. Yeah. If you have a powerful hand lens, you can even see these shapes. Yeah. And normally, the consistency may vary. And these are DY horizons. You may find also gypsum roses, so rows of gypsum crystals. Yeah, these roses, they are not from Tunisia, or they are not from these touristic places. They are one of my PhD thesis here near Lleida. Yeah, so you can find these crystals normally in the place of oscillation of the water table. When you have water table that is saturated with gypsum, you will have precipitation of these gypsum, big crystals in depth. Yeah, and then you may have also gypsum pendants. I had better pictures. Yeah, this is one type of gypsum pendant that you find under gravels, but you may have also pendants that are more fibrous. Yeah, they are also big wire rhizomes. Now, in this soil, sometimes you find also gypsum coatings on cracks. Why? Because, yeah, since imagine that you have a water table here. Well, this is not very good, this picture. You have here pendants of gypsum. But here you have a water table saturated with gypsum. So if you have a crack and you have an arid climate, you will have precipitation of gypsum, coatings of gypsum along cracks. And these are also the wire rhizomes. And you have fibrous gypsum. This picture is from Mongolia. And then you can get also some accumulation of gypsum in fibrous form. And these are also the wire rhizomes. Okay, I didn't put any picture of petrogypsic horizons because I don't have a good one. Yeah, I had some pictures in the field. But you cannot distinguish well the layers. Yeah, just a short, only one slide on the presence of gypsum in acid sulfate soils. You know, as you know, acid sulfate soils are those that are formed in reducing environments, and pyrite is formed with reduced iron and reduced sulfur. This pyrite, if the soil is waterlogged, yeah, reduced, nothing happens. The problem is when you start to aerate and drain these soils. It oxidates, and then sulfur passes to sulfate, and with calcium carbonate around will form gypsum. Yeah, so you may have gypsum in acid sulfate soils. Yeah, otherwise you have another sulfate that is jarosite. Yeah, this is, I think, the only micro photograph I have put here. Yeah, so this is from these pictures are from acid sulfate soils in South Australia. Okay. You may have also some floor-like gypsum. You may have massive accumulations of gypsum. In fact, this profile is one of these dry valleys, yeah, the bottom of these dry valleys, and you see the layers of these mud flows on this soil. So you have massive accumulations, but they are not cemented in this case. So you put a piece of this in water and it collapses. Yeah, they are floor-like. They have silty texture. Yeah, silty texture, or sometimes very fine sand texture. And yeah, this is the picture I have. Sorry, this is the only picture I have of. I'm sorry. This, and this. Now, I'm sorry. This is the only picture I have of BYM horizon. I mean, you see that is more or less the color of the upper layer, but from here to down, you may believe me, this is cemented. This is also near Lleida, yeah, in the Ebro Valley. So the test again is collapsing or not with water, yeah. But according to WRB and to soil taxonomy, already it is a petrogypsic horizon if it is weakly cemented. Why? Because gypsum is soft. Yeah. In mineralogy, the hardness of gypsum, yeah, is 2. Yeah, and diamond is 10. So gypsum is very soft. So it will break down very easily. Yeah. So we cannot determine or use the diagnostic of very strongly cemented. No. Yeah. But already weakly cemented is already a petrogypsic horizon. Another characteristic of many BYM horizons is that they are porous. Yeah. because we tend to think that cemented horizons are without porosity. No, BYM horizon can be very porous, can be even percolating, but they make like a network that is solid, that is continuous. Yeah. So these are some characteristics that we have to take into account with managing these soils. So problems. Yeah. Chemical fertility. Yeah, again, a lot of calcium, normally good, but we have phosphorus retrogradation in the same way as calcareous soils. Yeah, so we have to be careful with phosphorus fertilization. Another point is that due to the fact that we'll have a lot of calcium in the solution, it will be completely full of calcium, much more than with calcium carbonate. Why? Because calcium carbonate, calcium sulfate gypsum is very soluble. Yeah, so it makes that some bivalent cations like barium in some deficient, some sensitive crops will have problems of antagonism with some cations. The structural stability, low gypsum content, no problem, very good structure, but very high gypsum content. When we don't have clay to flocculate, the structure will be very, very, very weak. Yeah, so it creates this erosion, this wind-blown gypsum, these mud flows. Dissolution and crystallization, it dissolves and recrystallizes very quickly. So pore clogging results in higher capacity of the soil. And also gypsiferous soils, when they have a lot of gypsum, they tend to crust on the surface if they are bare, if they don't have vegetation. Water holding capacity, yeah, it will depend on the size of the gypsum crystals. Yeah, so if we have sandy horizons, these hypergypsic horizons is very high content of gypsum, 80%, 90% all sand, the water retention will be very low. If it's more silty, it will be higher. Yeah, so it will depend also on the amount of gypsum and the size of the gypsum crystals. Hydraulic conductivity is not generally affected, yeah, because gypsum do not cement directly, yeah, but the crystals are loose, so normal is not affected. Problems with buildings and with installations of drains and irrigation and so on. Yeah, concrete will weather, yeah, because it forms calcium aluminum sulfate with 31 molecules of water. So the increase of volume is enormous, and then it collapses, the structure collapses. Yeah, and also the steel also is also not resistant. Yeah, so you have to use building materials that are resistant to gypsum. And finally, calcification. Yeah, I would not build on a gypsum soil very high building because it will dissolve. These are the slope with these mud flows. Yeah, in gypsum rock. Yeah. This is calcification. Yeah, this is one of the profiles of my PhD thesis. Yeah, and you see that at given depth it collapses. So yeah, if you go with your tractor there on top of your field, there you will fall in a hole. Yeah. So these soils, yeah, have to be managed very carefully. Why? Because well, this is one of the first manual that was written in '76 by FAO. Management of gypsiferous soils. And in this graph, you see this gypsiferous rock, subsoil material with some cracks, as we said. And then if you irrigate, you will promote or will accelerate the dissolution of gypsum. Yeah. And then these terrains with collapses and with these holes, you will have to continuously level these soils. And then in the end, you have calcification, cavities, and you have a progressive enrichment of gypsum into surface. So These soils are considered in land evaluation schemes are considered not suitable for irrigation. If you want to irrigate these soils, you will be careful not to apply leaching fractions. For instance, if they are saline, do not apply leaching fractions because you will promote the dissolution of these soils. Yeah. So drip irrigation with very small irrigation bulbs will be more suitable for these soils. Classification, the diagnostic, gypsic, petrogypsic horizons, and again in WRB, gypsidic material when it contains gypsum without moving. Yeah. And also there are in WRB hypergypsic qualifiers for this very high amount of gypsum in these very highly gypsum-containing soils. In soil taxonomy, we have some gyps qualifiers or suffixes. In aridisols, you have the gypsic, yeah, and in insectisols, yeah, it moved, gypsic aplocheps, yeah, so it goes already to the subgroup level, yeah. And in WRB, you get already reference soil group, the gypsic soils, and you have the gypsic qualifier or the gypsic qualifier in other reference soil groups. Analytical problems. Well, you have very difficult dispersion of clays. So very often you don't have texture analysis of the soils. You have to trust your field texture, yeah, because, yeah, again, if you have a soil with 30% of gypsum, will you remove your gypsum to make the texture? No, because it will be meaningless, yeah. So there are two methods. I tested these methods and they work, but they are very time-consuming, but it is possible to apply them. These are methods that have a pre-treatment of the sample with barium chloride, so that theoretically, in each gypsum grain, you have a cover with barium sulfate that is insoluble. Yeah, so it is possible to perform this analysis. Yeah, but again, no, don't break your brains trying to disperse the clay into soils because it's very difficult. The determination of gypsum, again, is very difficult. The standard method is acetone, but acetone may be good for low amounts of gypsum, but when you have high amounts of gypsum, 80%, it's useless because acetone method, you have to dissolve, to precipitate, to dissolve again, and then, yeah, it's not accurate, not very accurate, and again, is not suitable for very high amounts of gypsum. There are other methods, dehydration, TGA, yeah, thermal gravimetric analysis, with different precision and accuracy. And 2 years ago, we published this paper, yeah, by a PhD student that finished her thesis some months ago, yeah, trying to test these methods with several materials. Again, avoid heating about 40 degrees. Very important. Yeah, if you suspect that your soil has gypsum, please warm the lab. Yeah, don't warm, submit the sample to more than 40 degrees. And also, again, when you have the test of the preliminary test of electrical conductivity, for instance, in an extract 1 to 5, it will give 2 already, 2.3 decisimeters per meter. And you may think that it will be saline, but no, because you will do the electrical conductivity of the extract and will give the same value. Yeah, so again, it's not saline. Yeah. And again, as with calcareous soils, extractable cations, when analyzing CEC, the base saturation here will be again 100%, and calcium has to be calculated by subtraction. Something I forget is that there are some trials to analyze the texture with laser particle size, so with laser diffraction, yeah? And yeah, it may result in better results than with the pipette method. But anyway, there are not enough results to make good advices in this way. Okay, I think that I arrived to the end. I thank you very much to all of you for listening, and I am open to any questions.
I think that Maria collected questions from the question and answers window, and she can now formulate to you. Please, Maria.
Thank you very much, Jorge. I think I will do this part of the job now.
Okay.
Thank you. So first of all, thank you very much, Rosa, for first of all agreeing to give this presentation. We know that you are very busy those days, and it was very, very kind from your side to agree to share with us this presentation. So thank you very much, and also thank you for your presentation. It was very comprehensive and very informative. So thank you again. And about the questions, so we collected many questions from the QR part. So I think I will begin with the first question that we have. So I think, Rosa, we have many questions you responded during the presentation. So if you already responded, just try to be brief and to remind people what you said during the presentation. So the first one was what are the criteria used for the classification of soil as calcareous soils?
So when it has calcium carbonate, if you have a significant, well, if you have 2% of calcium carbonate, not, but if you have 5, 10, 15, yeah, then it's calcareous soil. I didn't go, in fact, yeah, you're right. I didn't go very deep into this, but yeah, they appear regionally. So yeah, in our regions, yeah, you will have. Normally, soils will have in my region 20, 30, 40% of calcium carbonate soil. So, I think that the best solution will be looking for the calcare qualifier of WRB. I think that is 15%. Yeah, you may correct me because I don't remember well the figure. Yeah, but it will be this. Yeah.
Thank you. The second question, so here he said that you mentioned that calcareous soils will develop structure, but in arid regions, soils are very young as no water has gone through, and usually they contain very low of organic matter. So there is no much structure, at least in our arid zones. So any comments about this?
Yeah. You are right, because as you know, as you point well, soil structure is also promoted by organic matter, yeah, in the soil. And then if you have organic matter and the clays, you have calcium that is binding these components. If you don't have organic matter, yeah, you have only the clays, and then the structure will not be so good. But yeah, you're right. But if you don't have calcium, it's even worse. Yeah. So.
Okay. Yeah. Yeah, so thank you very much. The third question say, what is the inorganic carbon effect on the atmospheric CO2 emission?
Yeah, I didn't go with in this field. Yeah, indeed, I have now a project that is studying this. Yeah, and the effect of biological activity on formation of calcium carbonate in the roots and all this. Yeah, if you remember my first slide with this calcium bicarbonate, carbonate bicarbonate equilibrium, when you have precipitation of calcium carbonate in soils that the parent rock is not calcareous, calcium carbonate is net sequestration of CO2 from the atmosphere. Because the CO2 comes from photosynthesis or from the atmosphere. Yeah?
Yeah.
So, this CO2 is dissolved in water by bicarbonate, and then with calcium from I don't know where, then it precipitates. calcium carbonate. So it's sequestered there. Yeah. If we look only at the solution of precipitation of calcium carbonate, the sequestration is zero, it's neutral, because this process goes into two directions. So when calcium comes from a calcite and it dissolves and precipitates, then it has no effect on the CO2 of the atmosphere.
Yeah, thank you very much, Rosa. So the next question is, what are the symptoms plants show under calcareous and gypsiferous soils, and what makes these soils different from other salt-affected soils like saline, sodic, and sodic soils?
So the first part of the question, sorry?
What are the symptoms plant shows under calcareous and gypsiferous soils?
The symptoms. Well, the symptoms is what I said. So if I understand well, is what is the difference with saline and sodic soils, for instance? That plants do not show symptoms of salinity there. So the electrical conductivity, well, in calcareous soils, not, because the electrical conductivity will be very low. In gypsiferous soils will be around 2. The Siemens, and this, unless it's a very, very, very sensitive plant, plants will not show symptoms of salinity, with gypsum. Regarding sodic soils, this is more complex because you may have sodic calcareous soils, and also sodic gypsiferous soils. They are rare, but they exist as well. So you may have a lot of sodium in the exchange complex, and also calcium, and if sodium is more than 15% in the exchange complex, then it's a sodic soil, but the rest may be calcium, coming from calcite. So sodic soils may be also calcareous soils. And gypsiferous soils, sometimes they are saline because other salts are there, or sometimes not.
Yeah, thank you very much. I think you also responded a part of the next question that say, you said that gypsy soils are not saline, but why in the WRB classification dated in 2022, we find saline and sodic supplementary qualifiers?
Yeah, because sometimes you have salts in gypsiferous soils, but sometimes not. So they are like calcareous and sodic soils. So you have gypsiferous and sometimes gypsiferous and sodic soils, and sometimes gypsiferous and saline soils. It's common. But I know many gypsiferous soils that are not saline.
That's right. Yeah, thank you very much. The next question is, what are the impact of calcareous and gypsiferous on soil, physical, and biological properties of that soil?
Well, the physical and chemical properties I already explained, I think. Around biological properties, I didn't go much on that, because in fact, calcareous and gypsiferous soils, well, unless you have this 80%, 90% of gypsum, then you will have nothing else. They are soils that are eutrophic, that have nutrients, that have 100% base saturation. So normally they're not acidic. They have good, well, unless you have these acid sulfate soils, but this is another story. They are eutrophic, because the base saturation is 100%. And the only chemical properties are the ones I have explained in my presentation. So iron and phosphorus, iron in calcareous soils, iron and phosphorus in gypsiferous and calcareous soils, and also antagonisms with some cations when you have negatives.
Okay, thank you very much.
And well, and the biological fertility. In these soils you will have organisms adapted to the soils. And as I have said, in these soils, you will be surprised of when you see a thin section, the amount of faunal activity that you see in these soils, a lot of bioturbation. because all life in this environment, tested environments, is under the soil. It's where there is water or some water.
Yeah, thank you very much. The next question is, could you please comment on the size of the gypsum pendant and roses?
In the size of the gypsum crystals. Yeah, I have shown gypsum crystals and nodules of many sizes. It can go from coarse silt, yeah, when you have weathering of gypsum rock, dissolvent precipitation, you get very fine flour of gypsum on top, yeah. And then if you go deep in the profile, you get bigger and bigger crystals normally, yeah. Why? Because you know from your chemical lesson in undergraduate or in the school, the size of the crystals depend on the stability of the environment. So if you have a constant environment, the same temperature, a constant supply of water with sulfates and calcium, you'll have a slow growth of a gypsum crystal. But you have strong alternations of warm and cold or dry and wet. It's not time for the gypsum crystals to grow, so you have very small crystals. So normally, when you see a profile of with gypsum, you see very fine precipitation in the top, and then you get small gypsum roses more in depth. So you are getting bigger crystals the deeper you go.
Yeah. Thank you very much. Thank you. The next question is how to measure soil texture of gypsiferous soils.
Yeah, it's what I have said in my last slide. I was quite fast. Yeah, either you do it in the field with hand, yeah, do it like that. Because, yeah, in arid environments, gypsum is a part of the material of the soil. It's a particle, yeah? So all the physical properties will depend on the size distribution of the gypsum crystals. It's not something that are precipitated and you get rid of it. No, it's part of the physical components of the soil. Yeah, so you have to take into account these crystals when you have elements of gypsum. Yeah, or I mean more than 15. Then either you try with laser diffraction, yeah, or you try, if you really want to measure these sizes, you try with these two methods that you will have this presentation available. So you look for these references, and this is explain the complete method of coating, of the pretreatment to coat the particles with barium sulfate is explained in these methods, in these papers.
Yeah, thank you very much, Rosa. The next question is, do you mean that we measure the EC before depositing the gypsum with stannous?
I don't understand. Sorry. Can you repeat?
Neither me, I didn't understood this question. So do you mean, Professor, do you mean that we measure EC before depositing the gypsum with stannous? I think it was just a question about EC, the electrical conductivity measurements of gypsum, yeah.
Well, this EC thing is a bit tricky because, when I do my practical chemical, my lab practical with the first year students, we measure the electrical conductivity of the samples with an extract 1 to 5, and we say, if it's less than 0.2, the Siemens is not saline, and if it's higher, is saline or not? We don't know. We have to measure with the saturation extract. And then in the saturation extract, I mean, if you get with 1.15, you get 2, and you have some suspicion that in the field you find some white accumulations, and it's probably that this is gypsum. This is not salt.
That's right.
So you have to check with the field description.
Mm-hmm. Yeah, thank you very much. The next question will be about the calcium carbon determination. So it says that my question is, what is the easy laboratory method for carbonate calcium determination, and what is the concentration of HCl that normally where only 50% release is mentioned by you? And
Yeah.
he's asking about the reference, if you have any reference, because in their laboratory he said that he used just 10% HCl or 10 normals.
No, I mean 10%. 10%
Yeah.
is the one you use in the field. Yeah, to test the calcium carbonate. You put in the bottle with a dropping device, and then you go to the field. But for the calcium carbonate determination in the lab, with the Bernard method, with the volumetric method, you use calcium carbonate, hydrochloric acid, 50%. Yeah, you have to use 50% hydrochloric acid with Bernard method. It's very common method. Yeah? I think that it has another name in other places, but well, it's yeah. In a closed Erlenmeyer, you put sample, you put logarithm, and then you measure the CO2 that is released.
Okay. Okay, thank you very much. So the next question is, as mentioned, the calcium carbonate shows deficiency of iron, but honestly, in some cases, the orcars, the roots may restricted by the aeration caused by the cemented CaCO3. So the chemical solution like fertigation or fuller application just reduce the risk, while the physical restriction still remain. So what is the solution in your idea?
No, I mean, this, you are completely right. I mean, I have spoken about the problems individually, but yeah, if you have petrocalcic horizon at 10 centimeters, whatever, yeah, I mean, the problem is physical. And yeah, use crops with very, very limited rooting depth, or I don't know. I would not plant trees in this. Or, yeah, you have seen these pictures, yeah, with a machine, yeah, breaking down the petrocalcic horizon. But I don't like to break these horizons.
Yeah, yeah, thank you very much. The next question is, what are the limitations for routing of gypsum?
For?
Here it's mentioned what are the limitations for routing of gypsum. So I think
For routing of gypsum, yeah.
Yeah.
Yeah, good question. Good question, because I have said that they are normally porous, that hydraulic conductivity is not restricted, but routing, yes. Routing, yes, because, well, I have also said it briefly, because gypsum clogs the pores. And gypsum are like sun grains, okay? Lenticular sun grains. And then the packing pores are permeable, water goes through, but roots cannot go in. It's like you have the sand. If you have a compact sand, roots will not penetrate there. Yeah? So it behaves like a sand. And then sometimes it's difficult for the roots to get into these materials.
Yes, thank you very much, Rosa. The next question is you said no to eliminate carbonate when doing texture analysis, but to add more hexametaphosphates of sodium. Yeah. Is that right? Will that disperse the clay particles in soil?
Yeah, normally yes, we have no problem with that. Yeah, so we don't remove it because again, the particles of calcium carbonate are solid particles of the soil that determine all the physical properties. So we don't want to get rid of them when determining texture. So yeah, normally you put more sodium hexametaphosphate if it does not disperse and it will work.
Okay. Okay, thank you. The next question is for agriculture. Can you tell me if it's interesting to destroy a petrogypsic horizon or not?
I would say it depends on what you want and the next use of what do you want to use this land for. I would not break the petrogypsic. I would try to, because if you break the petrogypsic and then you irrigate, water will have a wonderful place to start a tunnel. Yeah. So, and to start to dissolve through this ridge or this hole you have made. So yeah. Another thing is that if you want to apply organic matter to the soil and you want to mix, maybe yes, but yeah, I think that it depends on each case and of you want to do. I will not be able now to say yes or not. Sorry.
Okay, thank you very much, Rosa. So I have the last question here for this webinar is people are asking for some references, and if you have any published articles that you can share with the attendees.
Well, I have from gypsiferous soil, I have some papers of mine you will find in Google Scholar by speaking about these physical properties, about this hardening when gypsum precipitates, but permeability is not restricted. And also this last paper about analysis that I think that is interesting because we compare different methods and we give a path to analyze gypsum, with the different methods. And if I can share some, but I think that every paper is on the net. If not, if you want to ask me through ResearchGate or so, people can ask me the papers and then I will send them with pleasure.
Okay, thank you very much, Rosa. So if you have any specific papers, just share them with me and with Maria, and then we'll be happy to share them with the attendees, or we'll make them like available on request. So anyone can request the references, and we can share it with them. So thank you very much again.
So this paper, this book on management of gypsiferous soils from Van Alphen and Romero. I think that is 76. The reference is in the presentation, but I think that is quite useful. And well, all the references that are in the presentation will be useful for them. Okay.
Thank you very much. Thank you very much, Rosa, for your time and for your interesting presentation. And now I will give back the floor to Jorge and Karim to close. Thank you very much.
Thank you, Isam. Dear Professor Karim, before you will close this, I would like to make a beg to Rosa, if could she, you have very perfectly described the cases of calcareous and gypsiferous soils, let's say mostly separately, but it is not infrequent that you have in the same soil you have gypsiferous, gypsic horizons and as well calcic horizons. And let's put some salts because from the INSAS. And it could be illustrative for the audience if you could quickly explain more or less how these different horizons relate spatially into profile.
Well, it relates with one of the first slides of the calcareous soils. I mean, if normally if you have a vertical leaching, you will have first a calcic horizon and then after a gypsic horizon. Why? Because calcium carbonate has less solubility, so it will precipitate first, and then afterwards you will have the precipitation of gypsum. If you have the calcium carbonate or bicarbonate saturated water table and also with sulfates and with salts, it will be the opposite. So we'll have first precipitation of calcium carbonate, after precipitation of gypsum, and after salt efflorescence and salt at the top. So it's like a chromatography. the same as I have explained for the dry lake. You will have horizontal chromatography, first carbonates, after gypsum, and after salts. Yeah. So the conclusion is that the relative position of gypsic and calcic horizons will give you the sense or the direction of the flow in the soil, if it goes up or it goes down.
Thank you. Thank you very much, and congratulations for your excellent presentation. And now I give the floor to Dr. Karim. Please, could you give the final remarks and closing the webinar?
Yeah. Thank you very much, Professor Rosa, for such an informative and useful presentation. You have helped deepen our understanding of complexity and potential of calcareous and gypsiferous fluids. You started a perfect introductory of calcareous and gypsiferous soil and their genesis, and you also elaborate their problem in terms of the nutrient deficiency, specifically iron and phosphorus, and so on. The main remarks of lab measurement were discussed. We noted, for example, indeed for texture, we should not remove when we measure the texture. It is a very useful remark. We notice how identify calcareous and gypsiferous in a simple way, just I want to mention it's on that there were many questions about the laboratory analysis and difficulties analyzes this kind of soil laboratory. I want to mention that we will come back in these properties and deeply discuss about laboratory measurement in the next webinars. For example, in the second webinar, we will discuss the chemical properties in this soils, challenges, and how can we analyze it and compare these methods. And we dive deeply to these measurement challenges. And also, we know that we have the big problem in the texture measurement in gypsiferous soils, and also electrical conductivity in different ratio. It remains. We will discuss in the next webinars, and also about texture measurement into physical properties. Today's session reminds us that managing the soils requires not only technical knowledge, but also collaboration and innovation. And the challenges are real that you saw in this presentation. But the solution we're waiting with the research and reach, especially when we work together, it is very important. I would also like to thank all participants to joining us and engaging with questions. It's a very good, very good questions and comments. Your participant interest and comment drive the success of initiative like this. As I mentioned earlier, this is just the beginning, and we go on to be are excited to continue this webinar maybe next week or next one. I don't know how can be scheduled the following the webinars. It's very important. And covering more topics relevant and sustainable soil management in our nano regions, North Africa and Near East, and also all of the regions that calcareous and gypsiferous soils predominant in these regions. It is very important. We hope to see all of you again in upcoming season. Let us keep sharing, learning, and building together toward a better soil and more resilient future. Thank you very much, and have a nice and great day for us. Thank you.
Yeah, goodbye.
Goodbye. Thank you.